Alright, let's work on the second problem of the day. Second problem is going to be this one. This is LeetCode problem number 148, sort list. Given the head of a linked list, return the list after sorting it in ascending order. And the goal is to sort it in n log n time and O of 1 space, according to the bottom. So, the naive solution would be to do something like a selection sort with 2 pointers, where you would say you hold 1 pointer at the beginning of the list, and you search for the smallest item, and you swap the 2 nodes. Pretty straightforward stuff. This would take O of n squared time, and O of 1 space still. And then you would just do it with the pointers. The question, I guess, is how do you do it with n log n time and O of 1 space? Could we do maybe a quicksort type of thing with the list? It's certainly an interesting proposition. How would we go about and do that? So we could find, let's see, we could choose the first element as a pivot, and this is just in this case pivot choice does matter in the context of quicksort if you want to have it as a constant n log n time, but I think in the context of this problem it's fine to just do like, okay, yeah, the head is going to be the pivot. I think it's fine. So this is personal preference. May not be optimal. Then for each element afterwards, either move it as the next item of the head or set it as the new head, and then recurse on the left and right sides of the list. The question then is, how do we know which side is which? Because it's not like an array where we have a sequential sort of access to the array. Are we guaranteed at least that the elements will be unique? Probably not. Let's just return null for now, and let's just do like a 111. And let's see if they're allowing us to have duplicate elements. If we have duplicate elements, then yeah. Since we have duplicate elements, we can't rely on that in order to really know exactly where we're at. We could do like a personal, like keep track of the array / window ourselves, which would be interesting. We could do that, yeah. It is an interesting idea. The problem is that doing this in O1 space, we could also, the other naive solution is to move everything into a list, sort that list, then override each node. This would take O of n log n time for sure, but it would take O of n space, right? If we just moved it into a list, sorted it, and then overrided the linked list. What else could we do? It's a good question. I'm kind of liking this quicksort idea, though my knowledge of quicksort is pretty bad. In any case, we can go ahead and try it out. This will take O of n log n time, O of 1 space, assuming that we don't keep too much information on it. So we could do a fun sort list. So this will be our, let's see, we need a left index. Well, we'll need a head pointer in this node. We'll need a left, which is an int, a right, which is also an int, and this will return a list node. And this will be sorts the list recursively, inclusive of left side and right side. Yeah, we can have it inclusive of both. Into var left is equal to, or, well, we know our left side will be 0. Var right is equal to 0. This will be a var because we need to increment it. So var runner is equal to head. And of course, if our head is equal to null, then we can just return null. And if head is, or head dot next is null, then we just return null as, or return head. If it has one element, then it doesn't matter. If it has no elements, it also doesn't matter. I say while runner dot next is not null. Runner is equal to runner dot next and right plus plus. And then we can say return sort list on the head, on left and right. And we'll have this as a list node non-nullable for now, unless we need it to be nullable. So now we can say, let's keep a reference to the original head. And then we can say var runner is equal to, or we can say, let's see, current head will still be head. For now, var current, let's see, tail is equal to head. Yeah, and then we'll do some fun stuff there. And we'll do a runner is also starting at the head, while runner dot next is not null. Val temp is going to be equal to runner dot next because we are going to be moving our, we are going to be setting our runners and stuff like that, so we're going to need to do some finagling. If our current head, or our runner dot val is greater than our our original head val. Otherwise, so if it's greater than our original head value, then since it's after us, we don't need to worry too much about it. So maybe the trick is just to do less than. If the, or since the runner is after our value, we don't care about it. I forgot what this kind of reminds me of bubble sort. Is it bubble sort that I'm thinking about? Where basically if the two values are, like, you just do comparison sorts at each value. Let's see. Because the runner is after our head value. Well, first we want to do while runner, or rather for I in 0 to left, runner is equal to runner.next. We don't know if it's going to be null, so move the runner to actual, move the runners to the actual window part. Wonder if there's actually a better way to do this. But all the other sorting methods don't really do what we need, right? Quicksort is sort of like the default sorting algorithm. I wonder if there's a better way to handle this, though. If there's a better way to do this than that. Let's see. Let me think. If we did... No, that would take memory. I was gonna say like patience sort, but no, patience sort wouldn't work either, because that takes additional memory. What is an in-place n log n sorting algorithm that we could potentially use instead? I'm not sure if there are any other than quicksort. Heap sort won't work. Because we need to store all the elements in an auxiliary data structure. Well, yeah, because we need to store all the elements in an auxiliary data structure. So that'll take O of n space, I believe. Heap sort would just make things so much easier, though. Hold on 1 second. Okay, so just did some more digging. Turns out that heap sort is O of n log n with O of 1 space. I think the idea is that if we use the space, complexity, then, or if we use the initial like actual data structure, then it's O of 1 space, right? So it doesn't involve actually like building a heap out of the elements. It's just moving the elements as if it were as part of a heap. So we could try this. So we need 3 pointers, a root or runner, a left and a right, and we say compare while the runner is greater than left, or the runner is greater than the right. Then we can say if the runner is greater than left, swap. If the runner is greater than right, swap. So the idea is that, for example, this 4 right here is less than, or is greater than the 2. So we swap it. So we set 4's next to 1 and 2's next to 4. And then, well, the problem is that we kind of need also a slower reference to the previous of left and right, and maybe runner, in order to fix the list. And then after, once this is done, we want to move the, let's see, runner up and the left and right according to their index, which we also keep. So if the index here is counted as 0, this should be 1, this should be 2, but yeah, okay. In that case, let's see. Let's do a dry run and let's see how this operates. So 4, 2, 1, 3. We'll use runner here, left here, and a right here. So R is runner, L is left, capital R is right. Then we set the 4's next to 1. And we set the 2's next to 4. The runner is still here. The left is still here. The runner, or the right, is still here. Now we want to swap the runner and the left side after they've been after the nodes swapped. So now the runner is here, the left is here, the right is here. Then we want to swap the runner with the right side. So now we have 1, which is still the right side, pointing at 4. The 4 still points at the 1 though. The 4 still points at the 1. And then we have a disconnect here. And then we have a 2, which is still the runner pointer, which now points at the 3. So now we need to make sure that, let's see, there exists a previous of the left and right, in order to set up the proper next values. So in that case, we would set up the left, or we would set up this 4 right here. We'd have to update this 4 also when they swap. Because before, in this initial thing, our previous of the 4 would be null. Where would our previous be? Our previous would be at the 4 and the 2, right? Because it would be the previous of the left and the previous of the right. Okay, so the previous of the right is just the left, so it doesn't matter. So we only need one previous of the right. Oh no. Because we need one for the right, because no, because they're always one apart, so just for the left, which would be a 4 in this case, which honestly is fine where it is currently, right? And then we don't need to actually move it then. We don't need to update it. And then we set the 4s next to let's see. So this is the previous left. And then we'll move it with that. We'll move it with the pointer. And then when we swap it, do we want to continue doing that? Not quite. We want to keep it actually where it is if it's swapped in to the left. So I think if we swap it to the left value, keep. Otherwise, if we swap out, reset to new. So now this 4 needs to set its left to the 2. And then we need to swap the values again so that now you're the runner. You're still on the left, you're on the right, and you're like that. So swap the runner and the right pointer again. And then we move up. So now this would be the runner. 2 or 1 times 2 is 2. Which is plus 1 is because this is 0, 0 times 2. 0 times 2 is 0. But we want the left side to be 1, and we want the right side to be 2. But beyond this, it doesn't matter, because 1 times 2 is 2, which is what we actually want, right? Is it? Actually, no. No, right, you're right. So 2 is... Let me think about this. One times 2 is 2. Plus 1 though, because of the previous, would make it 3. And therefore we would only really check that. Which doesn't make sense. Here we'd probably want to check that, at least those 2. Because then we want to swap with that one, with the 2, and then we end up swapping with 3. Let's do a different dry run with a different set of numbers, and then we'll see how we end up there. Let's see. Okay. -1 to 5 to 3 to 4 to 0. We swap well, we don't swap -1 with any of those. 3, 4, 0. Assuming that we keep that order. So we keep the runner here, we keep the left here, the right here, and it's going to be 2 times the value plus 1. So the runner here has a left of 4 and a right of 0. Does that sound right? Because 0, 1, 2, 3, and 4. Yeah. Then we would get preferably the first swap would be 4. And then the second swap would then be 0. Right, and let's assume that all the pointers work out magically. And let's just black box that for now. And do that. And then let's move on to the next value. The problem then is that, well, we don't have anywhere else to go at that point. Maybe the trick is that if we can't move further than our array, then we just use the last 2 elements, or further than our last element. So the idea is that we keep it at 5 and 4, and we don't move it, and then we instead just swap it like that. That might be the reason why we do something like this, where we keep this runner here, and then we just rather than doing the 2 times, like we get the left and right, we instead just keep the left and the right at the ends if we cannot go further. Okay, that might work. We could give that a try. I think that would be valid. The question then becomes, okay, then we need to keep track of the sort of layer that we're going through, the number of layers that we've gone through, which I think is fine with me. That kind of only just requires the index, right? Let's see. Does the index just double each time? I think it kind of does. Okay. So let's go ahead and... Man, this is going to be a little bit annoying because there's just so many pointers and references to think about. So we're going to need a slower reference than the left. We're going to need a runner, a left and a right, and then a lagging pointer to the left side, so that everything works out fine. Oh geez. Because like, for example, this one, right? If we wanted to swap it, we can set the left here for runner 3 right here. The point is that we need to set the previous of the runner, the previous of the runners next to the left, and we need to set the left, or the runner next to the left, right. So we actually need a pointer to the left, or to the previous of the runner, not necessarily to the left side. Though we might need a previous of the left side if they get separated too far. Right, like for example, this one. We want to set the previous of the right. It's next to this 4. And then we want to set this 3's next to this right. And then furthermore, we need to set your next to this 3 and this next to the to the 0. Ooh, this is messy. Alright, I'm gonna try to work on the implementation for a little bit and then I'll come back. Man, this one was more frustrating than I really expected. I basically gave up. I was thinking about using Quicksort for a while, but it was just the pointer manipulation that you really needed to do Quicksort, I think, with the linked list is just a little bit crazy. And heap sort as well. It's not great. So I look at the solution. It seems like the actual sorting algorithm to use is Mergesort, which kind of forgot was n log n and technically O of 1 space because if we don't count the recursive stack and all that stuff, right? If we're doing the top-down recursion method. So basically the idea is that we get the middle of the list and then we break the list into 2 parts and then we recursively call on each part. In the Java-based solution, it's a little bit not too obvious that this happens. I think mainly because this head is passed in by reference into the middle. And I think they manipulate it in there. But here I sort of explicitly say, okay, we get the next element from the middle, and then we set the middles next to null. So we actually split it into 2 separate linked lists, and then we call recursively on the left and the right side until all of them are lists of size 1, and then we slowly merge them together using just like the standard merge 2 sorted lists method. So that's how it works in O of n log n time. A little bit of a larger solution, but it works. In any case, I hope you learned something, and I'll see you for the next problem.